Okay, our video today is converting your weight to your mass. And let's use, well, we use red or whatever that color is. So again, the thing about weight, let's write this down. We'll write weight. Your weight will be different depending on what planet or moon or asteroid that you're on, right? And so most of us, right, the majority of everybody on Earth has never been anywhere else but Earth. Most people just look at the weight, right? But again, if you went to the moon, and there are people going to moon, there's the Artemis program. Artemis was the sister of Apollo. So that's happening in a couple of years. So those people will be on the moon, and their weight will be different, but their mass will not be. So again, weight right here is the force of gravity. It's the force of gravity on an object. And, whether it's a rock or a person or an elephant, whatever it is, right? So again, it's dependent. It depends, right? It depends on gravity. It depends on the gravitational force. Depends on gravity. And again, it will be different on the moon. It'll be different on Jupiter. You will weigh more on Jupiter than on Earth, but you will weigh less on the moon than you will on Earth. So let's just give an example here. Let's say you were 150 pounds. Now on the moon, you would be about 25 pounds. Not exactly, but we'll just use that, right? So here is the Earth, and there's the moon, right? So if you go to moon and you weigh yourself on the moon, you'll say, wow, I lost a lot of pounds. But your mass, again, right here, the mass will be the same. And we'll go over that. We'll do the calculations. The mass will be the same. All right, so let's calculate that now. We'll use another marker. We'll clear this out. There we go. And we'll use, why not? We'll use that color. Why not? All right, so let's say you're 150 pounds. Now the formula here is the weight, your weight is the mass times g, and g is the gravitational acceleration, right? So it's important though, with weight though, you don't want to use pounds. With weight, we need to use newtons. Isaac Newtons, right? Not Fig Newtons. All right, so we need to use newtons. So we have to the first thing we have to do, the first thing, like Dr. Seuss said, right? The first thing is we need to take 150 pounds and we need to convert it to newtons. And this one's an easy conversion because 150, a newton, by the way, we'll write newton here. A newton equals about, let's use the about symbol, about 4.4 pounds. It's not exactly 4.4 pounds, but we're just going to use 4.4 pounds. So a newton equals about 4.4 pounds. So we have that so far, right? Right, and let's now, okay, so got another marker here. Lost my page marker. I use green, dark green, like the Hulk. So we took 150 pounds. We converted it to newtons by doing 150 times 4.4. And again, it's not exactly 4.4, but we'll just use that. It's 4.4. And you'll get roughly 660 newtons. So if you weighed 150 pounds, you're 660 newtons. So now we have 660, because remember with the formula over here, the weight equals the mass times g, right? And g is the gravitational acceleration. So g is always going to be it's roughly 9.807 meters, and has a slash here. That means per second squared. But you don't need to know any of that. Just know we do use meters, but just know it just use 9.8. You can just use 9.8 and you'll get an estimate there. So we're always going to use 9.8. Remember, it's not exactly 9.8. It's 9.807 meters per. Remember that slash means per second squared. And mass is we're always using kilograms for mass. Right? So we have our mass, we have our kilograms, and we want to find the mass now. So we have our 660 newtons. And we know we don't have our mass, but we do have the gravitational constant of 9.8. So now we're just doing a little algebra here. We want to solve for m, and we just divide out, right? We're just dividing out. And we'll use another marker. Why not? Use that color. Why not? And so now we're going to know our mass, just from that simple calculation, it's going to be about 67.35 kilograms, because mass is always in kilograms. So that's your mass. That will not change. If you go to the moon, your mass will still be the same. Your pounds will not. So let's see that. Let's take a trip to the moon and see what we can do with that, right? So let's use another marker. We'll close that out. And when we do this, it's important to know that we were rounding some. So we're not going to get exactly the same answer, but we'll get the integer part will be the same. We'll be off by the decimal point, but it'll be, you'll see how your mass will be the same. So again, we said that on our mass was the mass. It was 67.35 kilograms. And again, we did round off the gravitational constant. So we're not going to get the exact. So on the moon, the only thing you need to know is that not the gravitational constant, but the gravitational acceleration on the moon, since the moon has weaker gravity than the Earth, it's going to be 1.62 meters per second squared. So we're just using 1.62. Now, the first thing you got to remember is we said that on the moon you would be 25 pounds, about. It's not exactly 25 pounds, so there's another way our calculations will be off a little bit. So 25 pounds we have to convert to newtons. So again, we're taking 25 and we're timesing it by 4.4, right? And we'll get roughly 110 newtons. So then we take 110 newtons, divided by the gravitational acceleration on the moon, which is 1.62, and we get about 67.9. So we're off a little bit because we rounded him, but you can see it's the same mass, 67, 67. So that's how we get mass from our weight. All right, great job.